about enabling renewables to power the world affordably, reliably and resiliently. We believe that with us, that all those three adjectives, or adverbs should I say, can happen. And also I personally believe that without us, they can't all happen. Essentially, the transition to renewable energy must happen. We've been seeing the effects of climate change all around us. By 2030, we need to reduce emissions by 30 to 45%, which is a phenomenal amount in a very short space of time. It's only 7 years away, and with the lead time of major capital plant and equipment and networks and grids, that's a very, very short space of time. That's just a blink of an eye. But it won't happen at all without solving the massive problem of large-scale electricity storage. Why? Because it replaces hydrocarbons with renewables, which are replacing dispatchability, that's availability on demand, with intermittency. It's also, so that means that the technologies that you need must be able to turn intermittency back into dispatchability and also into baseload, which is the always-on type energy. You've got to replace it. The energy transition is replacing synchronous with asynchronous. So your power generation is large rotating machines in a power station. The new renewable generation is all DC connected, whether it's solar, wind, tidal, or whatever. It's all DC connected. Solar interconnectors, DC connected. So you have lost your inertia in the system. So you need to create dispatchability on the grid, and you've got to create it in the right locations. Sorry, inertia on the grid. You're losing black start capability. Now, National Grid did a long project looking at distributed restart, and although their conclusions all say we must spend more time looking at it, and they've been saying that repeatedly for the last 4 years, their first engineering report, if you go back to that one, actually says that it's impossible using distributed systems and DC connected systems. If you think about it, when you've got a car trying to tow another on a rope, when the rope goes taut, the only reason you can move forward is because of two things. One is the momentum or inertia of the towing car, and the other one is the torque of the towing car. DC connected systems, even with grid forming inverters, have neither of them. So they can start themselves, but they can't start the neighbours. And what is more, they also proved that there is no conceivable way in which any system on any voltage level of the grid can start the next voltage level above on the grid, because it just doesn't have enough oomph. So black start, despite all their desires to do it distributed, has got to be from the transmission grid downwards. So renewable generation is at the right scale, but it doesn't do anything of the rest. Most storage is at the wrong scale, batteries, but they're at wrong duration. Everything that we've installed in the last 20 years is up to 2 hours duration. What happens after sunset when on a windless winter evening? How do you power the whole evening peak? Batteries will be exhausted by 6 o'clock. Wrong cost and wrong capabilities. So we need storage at the right scale, duration, cost, and capabilities. The solution is geological storage, because frankly you cannot build storage big enough without using geology to store the energy. These indicate salt caverns, aquifers, depleted reservoirs. There are other geologies that you can do. So one of our core technology on which we were founded used surplus energy to compress air underground, store it in salt caverns, and let the air out later on in order to regenerate the electricity. Same salt caverns are the only way in which you can store sufficient amounts of hydrogen cost effectively. So these ways you can actually store days or even weeks of duration of energy, and with hydrogen you can store longer durations than that. So why is the inertia such a big problem? Well, that's a picture of a nuclear power station. That's a person, just for the scale. All of that inertia in power stations, or most of it, apart from the nuclear, is closing down and some biomass. So you need to create that amount of inertia on the grid. Then there's the question of energy security, which our good friend, Mr. Putin, has raised up the priority list of policymakers. If you look at it, already the red countries are depending on imports during times of system stress. A time of system stress is when you have no wind and no sun, or less than 10% anyway, for a period of time. They're all importing now. By 2030, the orange ones will. By 2040, the light blue ones will. The dark blue ones claim that they will have enough for their own needs, but not enough to export. And now you can believe that claim if, for example, you believe that France, as of 4 years ago, was going to build 50 gigawatts of new nuclear on time and to cost. They still haven't got one completed. Not even Flamanville, which I think is 20 years overdue. So none of those will be able to export. The only ones with energy to export are the green countries. And they're not very big. And just a couple of months ago, Norway put in place legislation to say that in times of system stress, they have the right to turn off the interconnectors. And they're the ones with the most exportable energy at those times. So when these times of system stress happen, there's a famous scenario, the kalte Dunkelflaute, which is German for cold dark doldrums. When that low generation scenario occurs for up to 2 weeks across the entirety of that map. So if everyone's importing, who's exporting? The whole thing fails. You've got to store enough energy in country for your own needs. And that's particularly fortunate because most renewables can be generated in country as well. So building a renewable system without compressed air energy storage. The National Grid's Network Options Assessment said $2 billion worth of grid reinforcement for each gigawatt of new wind connected by 2030. But the announcement by Ofgem just before Christmas said that that's £3 billion of onshore grid reinforcement per gigawatt of new wind. And we're planning to install something like 60 gigawatts, going up to 120 by 2050. That's multiply that by £3 billion. And bear in mind that that cost is going up exponentially. Just a year before, it was only about $1.25 billion. Then you've also got to add on the procuring and connecting, the balancing and ancillary services, which in 2021 to 22 cost £8 billion. Just 3 years earlier, they cost 300 million. So that's a multiplier of 14.5 times. It's going up exponentially as well. Then there's operation and maintenance. That's 10% of the capex per annum. Half O&M, half finance costs. And it's going to increase. Breakthrough Energy in America says that the grid needs to triple, more than triple, 3.5 times, for the energy transition. And they conclude that that's too expensive for America. So what hope do we have? And that's only considering the electricity grid. None of these forecasts consider the hydrogen economy, because if you want green hydrogen, that too is powered by electricity. And that should add another 50% again to the electrical needs of the country. McKinsey concluded the energy transition will require a dramatic increase in capital spending on the on the electric grid delivered at an unprecedented pace. So it's widely recognised that, frankly, curtailment also rises with renewable penetration. There are a number of different studies that show that. You can go through these at your leisure, I'm sure. This is what I was saying about the £8 billion of balancing costs. Gone up more than 14 times more in just 3 years. And in fact, the 2021 to 22 figures so exceeded that the National Grid persuaded the government to allow them to defer some of the charges to the following year without actually realising that it will go up again on the following year, and they're just compounding the problem. Every single grid will have these challenges, which occurred on our grid from about 16% renewable penetration, because we already had about 3 gigawatts of long-duration storage with the pumped hydro schemes that we've got. If you have less pumped hydro schemes, that 16% threshold goes down. So what's the effect on bills? Electricity bills used to be 75 to 80% the cost of electricity. Now they're between 20 and 25%, and that's generous. They are currently 38% wholesale energy, 62% system running costs, but wholesale energy also includes the system running costs. They've already paid that premium, so therefore you've got 38% or 38%. And system running costs are rising exponentially. So the summary of the increased cost of the energy transition, very broad brush, is energy balancing is 25%. Stability, operability, power quality and all that sort of thing is 25%, and 50% is network reinforcement. With more grid, overcoming congestion and curtailment as being the main variables. Developments for compressed air energy storage. We found that Case was too inefficient. Huntorf, which is the first that commissioned in 1978, was 40% efficient grid-to-grid, burned 2/3 of the gas-fired power station. Macintosh 50%. So we developed a diabatic compressed air energy system that's 68 to 70% grid-to-grid, and diabatic system which is about 10 to 15% more than any other diabatic compressed air energy storage system on the market. Emissions are too high. Huntorf about 2/3 of the emissions of power station, and Macintosh about 60%, so therefore our adiabatic one is 0 emissions from day one, and our diabatic one is with dual fuel turbines that can start off on the gas grid, and as the gas grid decarbonises, so it can decarbonise because it can burn 100% hydrogen. Previous adiabatic technologies failed because they used obscure and expensive thermal storage, and thermal storage that destroys itself. Think of the liquid salt ones for the concentrated solar schemes. They eat themselves, basically, because liquid salt is very caustic. We perfected the thermal storage using off-the-shelf technologies readily available and fully integrated with the power and air subsystem. Then there are limitations in scale. Due to using salt caverns for air storage, there are perceived limitations much more than actual, because the salt basins in which the man-made salt caverns are made are very, very widely spread. So, but we're also going to develop other geologies, especially porous rocks, when we've got the resources to do so. In terms of efficiency, Huntorf and Mac, you can see our comparison there with the dark blue bars. The batteries numbers you won't recognise, because battery advocates lie. They like to say that their efficiency is 85 to 92%, but they measure their efficiency terminal to terminal, not grid to grid, and they measure it on day one, not lifetime average. The differences between terminal to terminal and grid to grid, the main one is about a 10% penalty for
for cooling, and that's in North Europe. Go into Saudi Arabia, and that's rather different. And 5% penalty for power conversion, AC to DC and back again. In terms, the difference between day one and lifetime average is that for power electronics and for the cells, both of those numbers are tripled by the time of swap out 8 years later, 8 to 10 years later. So therefore, the average penalty should be about 30% that you apply to the numbers that they claim. Cost effectiveness at scale and duration, this is talking about 5-hour plants where about 40% of the levelized cost of storage of batteries. Plant life, 5 times the plant life, but the most important one is this one. All of these services, batteries claim that they can do, even though that for Black Start that's not true. And also stability services, they provide synthetic inertia, which is nowhere near what real inertia does. But you need a different battery of the same size for each one of these. A synchronous system can deliver them all concurrently, and we're synchronous. So what's the best arrangement for this? If you connect all the renewables through suitable scale and duration storage onto the grid, then you can halve the size of grid connection for offshore wind, because you're taking out the intermittency before it hits the grid, so the grid doesn't have to be sized for the peak power. It's sized for demand. And that halves the size of grid connection, which gets around those 50% of costs of the energy transition. But what's more, if you use large-scale long-duration storage, and nearly all types, of which ours is head and shoulders the best, of course, I would say that, wouldn't I? All types of long-duration storage are naturally inertial. So that means that you can actually ring-fence the storage and the renewable generation and treat them together as though they were a power station, which makes system operability vastly easier and more reliable. It delivers dispatchable energy, that's variable on demand, that it carries its own inertia, its own balancing and ancillary services, stability service, power quality. It delivers all of those concurrently. We also develop hydrogen solutions. Hydrogen storage is very, very limited when you build it in metal. But one cabin can carry up to 10 million tons of it. This is hundreds of thousands of times. I think a tanker can carry 3 tons of hydrogen. Electrolysis hates intermittent power. Lots of people talk lots and lots of rubbish about using electrolysis to take out the intermittency of offshore wind. First of all, that doesn't solve the whole problem because it solves the intermittency input, it doesn't solve the variability of demand. Secondly, electrolysis becomes less efficient, shorter product plant life, and you need many times more electrolyzers per unit of output. So for example, if you've got 40% load factor offshore wind, you need 2.5 times as many electrolyzers per unit of output as if you have baseload electricity supply. If you have 1/3 load factor onshore wind, then you need 3 times as many electrolyzers. And if you have 1/6 load factor solar, you need 6 times as many electrolyzers. It's very simple. And not only the electrolyzers, but if you then have your nitrogen winning plant, concentration plant, you have your fuel synthesis plant, ammonia synthesis plant, that sort of thing, they all have the same issues, exactly the same issues. So we can deliver near baseload or baseload, depending on financial analysis. Baseload requires enough energy to go through the kalte dunkelflaute, and that's a fortnight's duration of energy storage. Near baseload, probably about 10 to 12 hours duration of storage. The capital cost difference is quite substantial, but near baseload, you'd be delivering baseload like this with occasional weather-related dropouts, which could be accommodated by storing end product. It just depends on the commercial analysis. Hydrogen is usually considered standalone, but we have discovered that the there are enormous synergies and cost effectiveness and efficiency improvements if you develop whole integrated systems, and in fact you can even take them off grid. Electrolysis technologies are too small. We actually have a patent on high temperature electrolysis that would be for massive scale electrolysis. That has yet to be commercialized and developed, but as soon as we've got the resources, we'll be doing so. So, hydrogen economy hates intermittency, reduces efficiency, plant life, and needs all sorts of more increased asset investment. Every single part of the hydrogen economy is struck in the same way. It also applies to the electricity economy. So, for example, desalination hates intermittency. If you can take out the intermittency before desalination or water treatment, then that will greatly improve the cost effectiveness of those plants. So you can do this around the world, looking at all the applications that they want for the energy. The more you integrate, the better it's going to be. And we can do all of that at infrastructure scale. The smallest we can do anything is about 40 megawatts. Now that's enough to power Crewe, a town of 60,000 people with its infrastructure and industry. So this is how that previous diagram works when you integrate the hydrogen into it. You've got the same, this does, the laser doesn't show up. You've got exactly the same diagram with the renewables storage of the grid, but you can actually cut that connection to the grid. It works well without it, and that gets rid of all sorts of costs and regulatory challenges. But you then use the electricity to power your electrolyzer, to power your fuel synthesis, to power the end-use plant. You can export direct to the gas grid with your hydrogen, or you can have these. The more integrated, the better. And every additional thing that you integrate becomes a much improved overall development. So thank you very much. That's how we try and make the whole energy transition affordable, reliable, and resilient. Any questions?
Yeah, these large-scale caverns, how do you ensure they don't leak?
Question is, how do we ensure that large-scale caverns don't leak? Salt is a wonderful thing. It's rather like glass. Did you know that glass is not solid? It's a supercooled liquid. That's why when you look at an ancient window side on, it's pear-shaped, because over hundreds of years it has flowed downwards. Now, it's also harder than concrete, stronger than concrete. Salt is the same. It will flow under geological pressure. That's the pressure of the weight of the rock above, which therefore means it seals all its own cracks. It's naturally hermetic. It's totally inert, so inert that the Americans use it very widespread ways for storing special waste, which is essentially any waste you don't want to ask what it is. As long as you keep the pressure inside the cavern, that flow will not close the cavern. It'll just keep it hermetic. They actually did an experiment, and I saw this where the experiment had done, where they deliberately put in so much pressure that it created cracks through the salt in an experimental tiny cavern. The next morning, the cracks had gone. It can be that quick. Any other question? Yes?
For example, from Stanford University, just out of curiosity, what is the pressure at which the compressed air is stored, and how is the safety concerns addressed in this?
The pressure at which the compressed air is stored depends on your geology. It doesn't depend on a set number. Basically, we are holding the air, also the hydrogen, at equilibrium pressure with the rock above. So the weight of the rock above is balanced by the pressure in the cavern. And so and that's 1.8 times hydrostatic pressure. So for example, if you're 100 meters deep, you need 18 bar. If you're 1,000 meters deep, you need 180 bar. And that's the depth to the top of the cavern. So there's an awful lot of soil and rock between the cavern and what's going on above ground, so you can continue with light activities above ground anyway, like farming and all that sort of thing.
So there are no safety issues concerning that?
No safety issues whatsoever, and it's not like fracking where you put in more than 10 times that amount of pressure with the deliberate intention to crack rock. It's also fracking pumps in sand and noxious chemicals, the sand to keep those cracks open and the noxious chemicals to leach out the hydrocarbons. We don't do any of that. All we're doing is pumping in water, dissolving the rock and pumping out the brine. There is nothing noxious in the whole process, nothing dangerous, and we're then going to fill it with air, and there's nothing dangerous about air either.
Thank you very much.
Just behind you, pretty close.
I'm curious about your efficiency graph that you put up, because you've taken into account the losses in conversion from battery to grid with all the control systems. What's your conversion? Because I couldn't remember you telling us. For the compressed air to electricity. You put it through a turbine, recip engine, what are you doing with it?
It does go through a turbine, and overall our plant efficiency is 68 to 70% whole plant efficiency.
And that includes turbine losses on compression and turbine losses on expansion?
It does.
Amazing.
And the key to achieving that is the thermal storage and the way in which we integrate the thermal storage with the power and air subsystems. And no, I can't go into details.
Because you will lose temperature. Which means your exhaust coming out is below zero. From 180 bar.
As I said, the key is in the thermal storage, making the whole thing adiabatic. There are people, three big companies about 10 years ago started up in America trying to claim isothermal compressed air was the way forward. Now, isothermal compressed air energy storage is different from adiabatic. Isothermal means that you do it at constant temperature. Adiabatic means that you balance the heat over the whole system, and that deals with your exhaust problem. Isothermal, you're extracting the heat at about 40 degrees, which is no good to man or beast, so it's going to be wasted into the atmosphere, which therefore means that when you come to expand the air and put back in the heat of expansion, it's going to freeze to somewhere below minus 150, and your brass monkeys will be terrified. So therefore, they talk about scavenging the heat from the environment, and you cannot scavenge that amount of heat. So therefore, isothermal cannot of itself work at any decent scale. Only adiabatic can work at that sort of scale, and that's what we've got. Anyone else?
What's the biggest megawatts you've got installed at the moment?
The biggest megawatts we've got installed. Now, first of all, the question installed, we're trying to do our first one. The second one, there's no limitation on how big we can do it. I've had proposals out there for up to 1.4 gigawatts. Because just like a power station, once you've got to the biggest size of turbine, you can double up. There's someone back here.
Hi, yeah, I think you may have just partially answered the question really. I was going to ask, what is the status of your technology in terms of development and commercialisation?
It is ready for construction, and even the ultra-conservative European Union says so at commercial scale. It's been validated by a few engineering companies, Costain, Fortum, who own E.ON among others, Mott MacDonald, Arup, Siemens, Mitsubishi, so not tin pot outfits. They've all validated it using their own methods. Siemens and Mitsubishi using their own equipment, both of whom have said that they can build the entire plant with their own equipment, and we know also that GE, Ansaldo, and various others can also do the same thing. So it's competitively buildable. And in fact, Mitsubishi even put in writing that they're prepared to consider an EPC guarantee against the first of a kind plant. Now, that tells you an awful lot about how low the technical risk is that they're prepared to take that on.
Just wondering about what sort of problems you might have with load sharing between asynchronous systems and synchronous systems, particularly with transient loads and transient responses.
Well, the great thing about the synchronous systems is that they absorb the transients and they reduce the rate of change of frequency. Do you remember the blackouts in 9th of August 2019 when 1 million people were blacked out, ranging from the commuter system in North London on the railways right up to a hospital in Cumbria? Well, that was caused by two simultaneous, well, 8 minutes apart, lightning strikes, one on a wind farm in East Yorkshire, one on a power station in Cambridgeshire. Now, because the grid was relying on so-called synthetic inertia from batteries to reduce the rate of change of frequency, we had blackouts. If it had been real inertia, we wouldn't. Now, why is that? The problems with the generators caused a spike on the mains. That spike on the mains went into the transmission grid. Now, synthetic inertia is a very fast response time, between 6 and 60 milliseconds. Now, that response time is a delay. That delay, even that smaller delay, was too long to affect the spike on the mains. So the spike just went straight through. And from these two failures near the East Coast, we got a cascade of subsequent failures all around the country because it was synthetic inertia, not real inertia. And yes, I've had that confirmed by a power engineer of one of those projects, even though National Grid denies it till they're blue in the face. So real inertia will take that spike on the mains, and because it's trying to move a large rotating system, that spike will gradually flatten out. So the rate of change of frequency, technically known as rock-off, will reduce. And so our naturally inertial systems, synchronous systems, will absorb those issues that come from the asynchronous ones. Anyone else? Apparently we've got 2 minutes left, so last chance. Speak now or forever hold your peace.
Have you identified any suitable sites for this storage?
Have we identified any suitable sites? Yes, we have. We've identified quite a lot of sites. Dozen or so in the UK, many overseas. We're in negotiations with a number of them. We're hoping to put in a binding offer on one of them within the next few weeks. We've got another two following on swiftly behind, and quite a pipeline of further opportunities in the UK and abroad behind that. We've also got scores and scores of companies around the world who have said that they'd like to fund follow-on plants. The challenge is the first one. So we've got some funders who are prepared to fund the first one as well. That's changed since the financial crisis, where people have realised that in order to get any decent returns on capital, they're going to have to accept a modicum of technical risk, which of course is misdefined by the financial industry. And we are just that modicum, so that has changed in recent years to enable it to happen, which is excellent. Also, the government is increasingly aware that they need to change the regulatory system in order to make it happen as well. We can be profitable in today's regulatory system, standalone on the grid, very profitable. And also, if we take hydrogen off grid, then that's the biggest, our integrated plants are the biggest step towards making green hydrogen competitive with blue hydrogen, and even competitive with natural gas. Biggest single step. I won't say it will get us all the way, but it's a big step.